So now we want to look at the integral from 0 to pi over 4 of secant squared x with respect to x. So whose derivative is secant squared? Tangent. So now we have tangent of x, and we're going to evaluate it from 0 up to pi over 4, which basically means we're going to substitute in pi over 4, and we're going to substitute in 0. The nice thing about pi over 4 is it's 45 degrees, so what's the tangent of 45 degrees? 1. Now we need the tangent of 0. The tangent of 0 is the y over the x, so if we take 1, 0, 0 over 1. So how much area is trapped beneath the curve of secant squared from 0 to pi over 4? 1. Exactly 1 square unit, which is kind of cool. Next, we want to look at absolute value. If you are integrating absolute value over a definite integral, it can be really tricky because absolute value technically acts as a piecewise function. So the best thing you can do with absolute value is to set what's inside equal to 0. Okay? So where's our equal to 0 mark going to be? 7 over 2, which is 3.5, right? Y'all understand that? Okay, 7 over 2. That's going to be where your vertex is. So we're going to take a look at absolute value here. And we know that at 3.5, it hits like right here. 4, 5, 6, 7. Okay, and that's an upward absolute value, right, you guys? Okay. So it looks like this and like this. So do you see how it's formed by two lines, and this side has a negative slope? So what would the equation of this line be? Do you guys know?
Oh,
it either has to be 2x minus 7 or the opposite of that. So it's negative 2x plus 7. So this side of the line is negative 2x plus 7. This side of the line is just positive 2x plus 7. So far, so good? So you have to kind of look at the graph and figure out whether it's equal or opposite there.
Minus 7. What? Yeah.
Oh, sorry. Yes, thank you. That is a minus 7. So usually what will happen is one piece of it will be the original and another piece will be the opposite. And your job is to kind of look at the graph and figure that out. So from 2, we're going to start at 2. So from 2 to that point right there, that's 7/2, I need to evaluate negative 2x plus 7. So you have to break this into two separate integrals. So from 2 to the vertex of 7/2, we are actually integrating negative 2x plus 7. And then you will always add to it the remainder. So I stopped at 7/2, and now I'm going to go up to what? 7?
Yeah.
Right? Okay, so that's 7. So now I'm going to calculate this area. So from 7/2 to 7, and that would be of 2x minus 7. It's tedious because you are doing two separate definite integrals, but that's basically the way absolute value is going to work every time. You're going to have to break it into pieces each time it comes down, each time it changes shape. Any questions so far?
I just have a general question. Is there any other type of graphs that are going to be broken up into pieces?
Absolute value.
Just absolute
Just
value?
absolute value, yes.
Okay.
Yeah, absolute. Anytime you want to integrate absolute value, you're going to have to look at it as a piecewise function. And the best way to do that is to look at the graph. And it's going to break where what's inside the absolute value equals 0. So that's how I know, like, this is going to be my breaking number. And that's pretty much going to happen every time. Okay, so if we integrate, we get the first one is what?
Negative x squared.
Negative x squared plus, and that's evaluated from 2 to 7/2. And this one is positive x squared plus 7x, right? And that's evaluated from 7/2 to 7. Oh, I just cannot get that minus right. Minus 7x. Thank you. Goodness. Okay. Double check. Are all my signs good? Yeah? So now we're going to evaluate these. We'll put 7/2 in, and that will give me negative 49/4 plus 49/2. So I've evaluated the 7/2. Then I'm going to subtract from that what I get when I evaluated it 2. So that would be negative 4 plus 14. That takes care of my first integral. Plus, parentheses, 49 minus 49, right, you guys? So this plus is what's between the two here. But it is minus when we substitute in the 7/2 here. Minus 49/4 minus 49/2. You have to be really careful here when you're distributing to make sure that when they come out of there that, and if you want, you could just type all of that in exactly like that and just see what happens. So I'll give you a minute to come up with an actual number there. I'm going to go ahead and distribute. It's a lot of numbers. All right. Anybody have any idea what that tallies up to?
No.
Not yet? Okay. Well, these make minus 10, right? Okay. Negative 49/4 and negative 49/4 is what? Negative 98/4? Does that reduce? What does that simplify to? Guys.
Wait, 49?
What does negative?
44 over 2.
44 over 2?
And then 22 over 1, so 22.
What?
What did you say? Somebody tell me. I'm trying to add these two together. Negative 49/4 and negative 49/4. What do they make?
Negative 98 over 4, which is 49/2.
It reduces to 49/2. Okay, cool.
What is negative?
Negative 49/2. All right. And positive 49/2 and positive 49/2 should be what?
0?
How about 49?
Yeah.
Right? You take half of something, you add the other half to it, then you have the whole. Okay. So that's going to be a positive 49. And that should take care of everything. So tell me what that tallies up to. Anyone?
I got 225 over 2.
Oh.
I got 29. I got 0,
So we cannot agree on this.
I
That's
got
what you're telling me.
6.5.
Can you
All
type
right,
this
okay.
one in on the
Okay,
calculator?
whoa. We are going to pause and we're going to come up with a consensus here, okay? So we agree that it's 29 over 2, right guys?
Yeah.
And we figured out that you can check it from the original right here and double check that in your calculator. You'll get right around 14.5. So let's do this guy. Remember that we can actually do this as an area problem. So we're going to find the area of the region bounded by the graph y equals 1 plus the cube root of x equals 0, x equals 8, and y equals 0. In order to figure out how to set this up, you really need to be able to visualize it. So go ahead and in your calculator graph 1 plus the cube root of x. 1 plus the cube root of x. Just so you can get a visual on it. I think, tell me if I'm wrong, I think it looks something like this.
Yes.
Yeah.
Does it? Okay. It's like a sideways cubic. Is that right?
Yes.
Okay. So what we're looking at is this graph. We're going to go from x equals 0, so that would be this line right here, over to x equals 8, so we'll just pretend this is 8. and we're going to trap it with y equals 0. So we're trying to find the area of this piece right here. Make sense? Okay, so this is our main graph, so that's what we're going to take the integral of. We're going to take the integral of 1 plus the cube root of x with respect to x, because we're trapping to the x-axis. And we're going to go from here, which would be x is what?
0.
Up to x equals 8. So from 0 to 8. So this shouldn't be too bad. Those are going to be nice numbers to take cube roots of. So if we integrate that, we get x plus, and remember you have to think of this as x to the 1/3. So we add 1 and we get 4/3 and divide by 4/3 and you get 3/4. So we have 3/4 x to the 4/3. We're going to evaluate from 0 to 8. We substitute the 8 in. Well, I'm going to go ahead and put it back in cube root form. It's just easier for me to understand. So x plus 3/4 times the cube root of x, and then raise that to the 4th power. So now we'll substitute in the 8. So we have 8 plus 3/4 times, what's the cube root of 8?
2.
2, and 2 to the 4th power is
16.
16. So there's the upper limit of integration. Minus, we'll substitute in 0, and we'll get 0 plus 3/4 of cube root of 0 is 0, 0 to the 4th is 0, so times 0. So we really have 8 plus 12 minus 0 minus 0. So it looks like that area is 20. So that's not too bad. You can check that in your calculator. For our final example, we want to find the area of the region bounded by the graphs of y equals 2x squared minus 3x plus 2, so that's a parabola, x equals 0, x equals 2, and the x-axis. So I'm going to go ahead and just kind of like graph it up here for you guys. That is an upward parabola, so it hits here. And I think if we look, it looks something like this, right, you guys? I don't know if anybody's looked at it yet, but something like that. And we're just going to go from 0 to 2. So we're looking for this area right here. 0, 2, and we're bounding it here. So it's that little area there that we're looking for. Is that what you're asking? Yeah. Okay. So now we're going to integrate our main function, 2x squared minus 3x plus 2 with respect to x, because we are trapping by the x-axis. And we're just going to go from 0 to 2. So what's the integral? 2/3 x cubed minus 3/2 x squared plus 2x, right guys? From 0 to 2. So if we substitute in 2, we get 8 times 2/3 is 16/3 minus 6 plus 4, right guys? Minus 0 cubed is 0, minus 0, plus 0. So that ends up zeroing out. So we have 16/3 minus 2, which is the same as 16/3 minus 6/3. So is the right answer 10/3? Yes. Yay. So that pretty much wraps up the first fundamental theorem of calculus. Did anyone check it with the second trace function?
Negative 10/3 is what's on
I got positive.
I know that's wrong.
I thought you put the upper and lower limit in backwards.
Yes,
Yeah,
yes.
that's what'll happen. Yeah. It should be positive because it seems to be trapped up here. Alright. So does anybody have any other questions?
How do you know you've already answered this.
Hey guys, hang on a minute.
How do you determine which is upper and lower? Because I just went in the order it was in the problem and put the 0 on
This
top.
is always the lower
Yes, ma'am.
and this is always the upper.
Yes, but like which numbers, like when it gives you x equals 0 and x equals 2.
Oh, if you're not told otherwise, you always do the lower limit as the smaller number.
Okay.
Yes. The lower limit, unless there's a specific reason you're told to do it backwards, you always do the smaller number as the lower limit, the A, and then the larger number. Because you just imagine we're going to accumulate our area as we go from left to right. So, all right. So for this practice, we're gonna do 3 through 41 odd. And in class next time, we'll look at the second fundamental theorem of calculus.